But yeah, I'm going to talk about how Beam can serve large models. So when we think about Beam ML, there's several different components that you can kind of think about Beam fitting into. So this is a simplified version of the typical ML lifecycle you can think about, where you've got ingestion, data validation, data preprocessing, training, validation, and model deployment. And when you think about like where Beam fits in, I think the data validation and data pieces are pretty obvious. It makes sense of like you want to process large scales of or large amounts of data and do actually pretty parallelizable operations on them. It's kind of a natural fit. Model training, usually not the best fit. You can do some sorts of online training, but iterative training, if you're doing it at larger than single box scale, is going to be hard on Beam. And then what I want to spend most of today talking about is kind of the model validation and model deployment pieces. So this is basically deploying your model to do inference, either to do your validation where you're running kind of known examples against your model to generate statistics and determine how your model performs, or you're actually going and deploying it in kind of real world useful pipeline where you're going and doing some sort of task. So to kind of give background, I'll start with just what basic inference using Beam looks like, and then we'll progress from there to what Beam does to make serving large models easy and how you can go ahead and consume that. So when you think about distributed inference, whether you're talking about Beam or you're talking about any sort of large scale distributed system, if you're deploying your model, you're going to run into some set of problems. Obviously, like you need to be able to load your model to have it be useful, and you want to do that in a way that is efficient, and you're not loading too many copies of your model. You're not loading too few copies, and you're kind of taking advantage of your system. You want to do some sort of batching almost always. Models are much more efficient when they're running on batches of data. The particulars of the batch size are model dependent, but especially if you're running with accelerators, you're going to get a lot of benefits out of batching your data. You need to update models usually. It's pretty rare to deploy your model, especially in a streaming context, and just let that model be stagnant forever. And very often today, and this has certainly been talked about in our keynotes and some other talks, you want to deploy multiple models. This is really common, and I think like something that is not necessarily trivial if you're rolling something yourself. All of these, if you're rolling it yourself, whether you're doing it just on normal compute or if you're doing it within the context of Beam, are pretty tricky actually. It involves managing your infrastructure and kind of setting up multiple processes maybe, and it's just like not super trivial to do at scale in a way that makes sense. And we saw, especially with Beam, a lot of people rolling this themselves and kind of doing the same things over and over again. And so out of that, we introduced the RunInference transform, which some of y'all may be familiar with. But basically, RunInference takes care of all of the boilerplate tasks that people were performing over and over and over again. And especially, it takes care of all of the kind of things that are specific to Beam. So an example that I'll mention later is Beam might spin up a bunch of different threads per core on a machine, but it's pretty much always more efficient to share your model across threads. So RunInference just does that by default. And there's all sorts of like little Beam optimizations that this transform makes to abstract away the difficulties of running inference at scale and make it really just simple to get up and running with just using config. So in practice, here's an example of what this looks like. Really, the two key concepts here are the transform itself, RunInference, which I talked about, and the model handler. And as you can see, this model handler is just configuration. All you're doing is telling it how to go ahead and load your model and maybe how to invoke your model. So you don't need to worry about deployment. You don't need to worry about like the topology that you're running on, the particulars of the machine, anything like that. Beam will take care of it all. So before I get into kind of the large model piece, I'll just like give an example of what it looks like to run a pipeline. I'll be pretty quick because I want to spend most of the time on the memory management piece. But skipping the dependencies, you can see here, like I just described, you're going to define some sort of model handler. In this case, I chose to use a Hugging Face pipeline, which is basically just like a wrapped version of a model to perform common tasks that Hugging Face puts out. I'm doing a translation task. I chose this model just because it fits in Colab memory, which is pretty small. And you can pass other arguments. Not all of this is actually necessary. It's just kind of showing how you can do it with this particular model handler. In this case, I'm just using kind of synthetic inputs, but you can imagine in a real world scenario, you might have things coming in from Kafka or PubSub or something. But in this case, because it's a translation model, I've given it translation inputs and tasks to do. This is just printing it, so it's not too exciting. And then this is our whole pipeline. So note here that if you swapped out this with a real source and this with a real sink, this is actually like a real useful pipeline that you might deploy and use. Maybe you need to do some sort of like consistent text translation, and it's like 5 lines of code if you count I guess like 7 if you count the model handler, something like that. And you can see it does the translation, and I think it's good enough. You'll get better translations with better models. So that's what kind of normal vanilla inference on Beam looks like, and kind of normal model serving. So now I'm going to get into kind of the meat of the talk, which is digging into what Beam does to make serving large models easy and effective. So kind of as my motivating use case, we'll think about text summarization model. And to start, we're just going to imagine a small to medium-sized LLM, basically like something you can fit into memory as much as you want. And in this case, I just have it summarizing food suggestions, and it does fine on the kind of simple task. So you don't really need anything super special here. So when you think about like a Beam runner, this is what a Beam Python runner usually looks like. I have the asterisk because it's not part of the Beam spec, but in practice, this is what it usually looks like. You've got probably a bunch of different worker processes, usually one worker process per core for Python because of how Python does concurrency. That lets you leverage the concurrency most effectively. And really, if you think about like, if we were just spinning this ourselves, this is what we want our model configuration to look like. Because it's a small model, you can fit a bunch of them into memory. And these are basically the same. So you don't need a whole lot of special stuff here. And so this is pretty easy for Beam to handle. And like I mentioned, the only thing that Beam does here that is kind of different or you might not think of is it shares the model across threads. So when you load it, even if you've got all of these worker processes, they're all just sharing a single copy of the model. That's because basically you can do that for no performance hit and it doesn't blow up in memory. So it's better in pretty much all cases to do that. All right, let's talk about a more interesting use case though. So let's say that your model is not performing well enough. So I changed the input here, and instead of just liking pizza, I'm liking tacos now too, and it just doesn't get it. So I want a better LLM. So you have a bunch of different options here. One, you can go back and you can retrain your model, or try to find a different model. You could, I don't know, maybe like set up a second model or something to validate, or do all sorts of things. But very often, the right thing to do is just use a bigger model that is better trained. And so it's useful to be able to go from your existing pipeline to a pipeline that has a larger model. And ideally, you wouldn't have to really change your pipeline much beyond that. So in this world, our ideal model configuration looks more like this. You have a single model sitting in the center of your VM and kind of its own dedicated process. All of these other processes are still doing I/O. You don't want to just have one process because it's not going to do I/O effectively. And if you have anything else going on in your pipeline, like pre-processing, post-processing, you're bottlenecked on this single process. So you still want a bunch of different processes, and you just kind of want your model centralized. So imagine you were doing this kind of yourself, either with Beam previously outside of RunInference, or using just like tools that you can spin up on your own cluster. Probably you would have to do a pretty significant amount of work to change from the last configuration to this configuration. You need to figure out some way to do the inter-process communication. You'd probably just end up switching your machine, and you'd probably use a larger machine. And that's not a very cost-efficient decision, and it's not necessarily a great option in all cases. It might be that you can't even find a machine with enough memory to accommodate your model in some cases. Unfortunately, this is still our Beam worker though. So ideally, we would be able to map our Beam worker to this configuration. And RunInference introduced a mechanism to do exactly that. So RunInference has the ability to spin up a dedicated inference process that just sits, it holds your model, and the other worker processes know how to talk to it. Basically, at startup time, the workers will kind of elect a leader that spins up this process, and then they'll all get references back to this original model using Beam's multi-process shared utility. So this reduces your memory. It does come at a slight cost. You have to do this kind of inter-process communication as opposed to the original case where you just had your model sitting in each individual process. In practice, though, we haven't seen that be a significant barrier. Usually, the cost of I/O is much more significant than like into and out of the box than the cost of kind of shuttling bytes across the process barrier. So yeah, like I mentioned, if you were spinning this yourself, you need to do a kind of full serving topology change. But with Beam, it's super trivial. So if you'll recall, this was what a model handler looks like. And this was kind of what it took to serve your model in the vanilla use case. But because we've separated our model configuration from our actual like serving topology, all you need to do to change how you're serving the model is add a single parameter to your model handler, and it'll switch the topology and kind of handle all of this under the covers. If you're not using Beam's built-in model handlers, so like let's say you want to write a model handler for JAX and Beam doesn't support JAX out of the box yet. Beam has a mechanism where you can write a custom model handler. So this is what a custom model handler would look like just kind of by itself. You have a way of loading a model and then a way of running inference. To share the model across processes, all you need to do is add this lifecycle method, and that will switch the topology to the kind of central large model process. And that's all it takes. So it's 2 lines of code. Now, let's say you have a medium-sized model and you want exactly 4 copies of the model in memory. That's still like a reasonably common scenario. All you need to do is add another lifecycle method, and Beam will take care of all of those pieces for you. So with just kind of basic configuration, you're able to take your model serving topology and change it. You can play around with it. You can try different topologies, and all it takes is like 1 or 2 lines of code. So this is really useful if you want to make pivots as you're going. Maybe you started with a larger machine, a larger box with a bunch of memory, and then you decide, oh, that's too expensive. I want to use a smaller one. Or maybe you just want to size up your model as you get new data, or you find a better model on Hugging Face. So that's roughly how that piece works. But let's say that I need multiple models in my pipeline. Let's say, for example, that I need a model per customer, and maybe I need like 5 models, maybe I need 50. And examples of where you might need this are if you've got specifically trained models. So maybe you've got one model that's very good at text summarization for food reviews, and another one that's really good at text summarization for travel. That's the use case here. Or kind of the more common use case I've seen is you've got one customer who doesn't want their data used for a model that is consumed by another customer. You might have something like that, where you still want to run in a single pipeline, but you want to make sure that you're not mixing and matching data across customers. So we've gone from kind of our ideal model configuration where you've got one central model to one where you've got maybe a bunch of different models sitting around memory, and you don't even necessarily know like exactly how many it's going to be. That might change over time. So Beam, again, has an answer for this. So we introduced something called a model manager. A model manager sits in a central process, very much like the large model setting that I talked about earlier. But instead of just holding a single model, it holds references to other dedicated model processes. So basically, like a worker process will talk to the model manager and say, I want model X. The model manager will either return a reference to model X if it's already loaded, or it'll say, oh, model X isn't in memory yet. Let me go spin up a process, download it. You can also put controls on how many models you have in memory at once. So it'll offload it and handle garbage collection and everything like that as well. So basically, the summary here is, the model manager is fully empowered to handle onloading and offloading models as you need. And it will, again, take care of all of the tricky pieces of dealing with distributed systems, dealing with memory capacity and all of those pieces. And all you need to worry about is defining which models you want to map to which records. So again, This is just configuration. So this is our like basic model handler example, again, with nothing special and just a single model. If you want to change this to the per key model, like I mentioned, all you have to do is add a second model handler for whatever model you want. That's model handler 2 here. And then define your per key mappings. So in this example, if you've got a record that is keyed by keys key 1, key 2, or key 3, that will map to model handler 1, or the model represented by model handler 1. And if you've got keys represented by foo, bar, or baz, those would map to the second model handler. And that way you can control the flow of traffic, and Beam will handle all of the memory management. You can also, of course, just have different transforms. You can have different run inference transforms, each defining kind of different model that they want to run inference against. And that works great too. But this allows you to encapsulate it in a single step. And especially for cases where you've got a bunch of different models, it makes observability a little bit easier, I think, and kind of avoids you having to keep track of 10 different stages. So pros and cons there, but I think it's a good option for a lot of use cases. So let's talk about specialty hardware. It's really common to want to run your inference on GPUs or TPUs. And obviously, like, the availability is dependent on the runner. So not all runners are going to have access to all hardware. And if you're using the local runner, you probably don't have a DPU attached. But for cases where you do have hardware available, like GPUs or TPUs, Beam can help. So Beam's got a bunch of different primitives for making this part easier. And one is something called resource hints, which allows you to say, I just want to use a GPU for this part of my pipeline, and I want to use a CPU for the rest. That can be really helpful for driving down costs. And I think especially if you've got a big pipeline, it is really expensive to use a GPU for the whole thing, but it's a lot cheaper if you just need it for a certain part. Also, at the run inference level, we've got built-in detection for are you using a CPU or GPU, and responses at the model handler level. And again, this allows you to decouple where you're deploying your model from what model you're deploying in your pipeline logic. So it's kind of in a similar vein to the memory management piece of you shouldn't have to worry about where you're running your model. You should just need to worry about which model you want to use. And then the last piece, and really why I included this in this presentation, is the large model setting that I mentioned earlier can actually be really helpful in GPU contexts too. So very often it is helpful to load and unload data to a GPU from a single point rather than having a bunch of different models sitting in different processes. GPUs tend to perform better if you co-locate the data and just kind of unload it and offload it from a single location. So if you use the large model setting, that'll just happen automatically, and you don't need to worry about any of those pieces. There's other ways to do this too. NVIDIA's, I think, like working on this problem, and they introduced NVIDIA NPS about a year and a half, which allows you to more efficiently run inference from a bunch of different processes. But there's still cases where it can be pretty helpful to just have the single process. And again, like all it takes is a single configuration parameter in your model handler logic and you're golden here. The last thing I'll call out is we have a bunch of examples in the Beam repo. I included a link here to a bunch of notebooks. Basically, it looks like this. So the example I showed today is in there, along with a ton of other examples with different frameworks. It shows running inference locally, running it remotely as part of a pipeline. It shows multi-model situations, model updates, kind of everything that you would need to get up and running with machine learning. So that's everything I had prepared.